This is Rizwan Azim, and I will be taking you through the air conditioning part of the course in refrigeration and air conditioning from this week onwards. Up to now you have already gone through the refrigeration part, and if you look at the course CLOs, CLO number 1 applies to what you have covered so far in refrigeration, and from this point onwards we will start with topics which relate to CLOs 2 and 3, and then finally CLO 4 refers to the contents of your practicals. The CLOs or topics are also provided to you separately for convenience, and if we look at the first topic in CLO 2, that is psychrometry, and that is what we are going to start with. Before we move on to that, when we study air conditioning, basic thermodynamics concepts will be required. In addition, at some point we will also make use of your knowledge of heat transfer and fluid mechanics. So now let's move on and again remind ourselves of how can we differentiate between refrigeration and air conditioning. Refrigeration involves removal of heat from a region which is at a relatively lower temperature, and then rejecting that heat in a region which is at a higher temperature. And to achieve that and satisfy the laws of thermodynamics, we need a net power input into the system. Air conditioning, on the other hand, does not restrict itself to cooling only. Depending on your requirement, air conditioning could be providing heating, for example during the winter season. In addition to the temperature, there are other factors which are also accounted for in air conditioning. For example, the relative humidity, the velocity of motion of air within the conditioned space, radiant energy levels, the amount of contamination that is tolerable, and even how much noise attenuation is required according to your environment. So now we move on to the first topic, that is psychrometry. Psychrometry is the study of the thermodynamic properties of moist air. Moist air is simply air in which water vapor is present, and we can consider the moist air to be a binary mixture, dry air and water vapor. And for the typical conditions of air conditioning that we come across, each of these components can be considered to behave as an ideal gas, and the justification for that is that the air, that is the dry air, behaves like a perfect gas because its temperature is high relative to its saturation temperature, and for water vapor we can assume it to behave like an ideal gas because its pressure is low relative to its saturation pressure. And once we assume that ideal gas behavior is applicable to these constituents, we can apply the relevant mathematical equations that are already known to us to find out or estimate various properties of the moist air. The typical properties that we will come across when we study air conditioning are, starting with the mixture pressure. The mixture pressure, we are very well aware of this basic equation, that the total pressure of a mixture of gases is the sum of the ideal pressure of those constituent gases. And because we have a binary mixture, the total pressure is the sum of the partial pressure of air and the partial pressure of water vapor in that air. And we are using the symbols subscripts A and V to designate the two constituents, air and water. The humidity ratio is defined as the mass of water vapor per unit mass of dry air, and we are using the symbol capital W to designate that, and in a SI system it will have units of kilogram per kilogram dry air, and when we write it as a numerical value, kilogram of dry air is shortened to kg dA. And because we are saying that both the gases behave like ideal gases, we can use the ideal gas equation to designate the mass of water vapor, which will be equal to PV upon RT, and similarly for dry air. Because the two constituent gases are occupying the same volume and are at the same temperature, these terms will cancel out in the numerator and in the denominator, and we will be left with the ratio PV by RV divided by PA by RA, and R is the gas constant, which is the universal gas constant divided by the molecular mass of that particular gas over here. And what we can do is substitute the values of the molecular masses of air and water vapor and the universal gas constant in this equation, and we will get a resultant expression for the humidity ratio, which is 0.622 times the partial pressure of water vapor divided by the partial pressure of air, which is the total pressure minus the partial pressure of water vapor in the air. Relative humidity, I'll just read off the definition first and then try to explain it. It is the ratio of the mole fraction of water vapor in moist air sample to the mole fraction of the water vapor in a saturated moist air sample at the same temperature and pressure. If you have a sample of moist air and if you add water vapor to that sample, the partial pressure of water vapor in that sample will increase, and you can keep on adding this water vapor into the air sample, but you will reach ultimately a point where the air will not be able to take up any more water vapor, and we will say that the air has become saturated. So if we differentiate between the two states, then you will have a maximum possible vapor pressure at the saturation state at a given temperature and total pressure. And again we can use the ideal gas equation, that PV is equal to number of moles into RT, where R will be the universal gas constant. So the number of moles will be PV upon RT, and if we take the ratio when the moist air sample is not saturated and divided by the number of moles when the moist air sample is saturated, again the universal gas constant, the volume and the temperatures will cancel out because they are the same, and only the partial pressures will be left, and that ratio will give us the relative humidity. The relative humidity expressed as a percentage will be PV upon PV sat into 100, and obviously it will vary in numerical value from 0 to 1 or as a percentage from 0 to 100%. If there is no moisture present in the air, it's completely dry, then the relative humidity will be 0, and if the air is completely saturated, then if PV sat becomes equal, PV becomes equal to PV sat, then phi will be equal to 1 or 100%. The enthalpy of the moist air sample again will be the sum of the enthalpies of dry air and water vapor contained in the air, and the total enthalpy, we have the equation, we are designating the total enthalpy by capital H, which will be the sum of the total of the enthalpies of air and water vapor. If I want to use specific enthalpy, I can find out the enthalpy as a product of the mass times the specific enthalpy, and we can do that for air as well as water vapor, and the resultant equation that we have is capital H is equal to MA HA plus MV HV. Now if I divide the right hand side and the left hand side throughout by MA, what I will get is the specific enthalpy of the moist air, and that will be energy per unit mass of dry air. On the right hand side, MA will cancel out in the first term, giving us HA, and in the second term on the right hand side we will get the ratio MV by MA, that is mass of water vapor divided by mass of dry air, and that we have from our previous definition is the humidity ratio, and we can appropriately replace MV by MA by the humidity ratio W, and as I said, it will be having units in the SI systems of kilojoule per kilogram dry air. We can make a further simplification, and that is HA can be approximated as the product of the specific heat of dry air multiplied by the temperature in degrees Celsius. And to do that, we will assume that the reference state is 0 degrees C, where HA is 0. Now with that selection of reference state, HA can be replaced by CPA times T. CPA is the specific heat of dry air, which is 1 kilojoule per kilogram Kelvin. The temperature over here will be in degree Celsius. And the other simplification that you can see over here is that HV has been taken to be approximately the same as Hg, and there must be a justification for that as well, which we can observe if we look at the Mollier chart. If you look at the Mollier chart, I've shown you 2 points in the Mollier chart. One lies on the saturated vapor line and the other is in the superheated region. If our actual state is in the superheated region, we can see that at the constant temperature, the value of the enthalpy is almost the same over in the superheated region at this point and at the saturated vapor line, because of the almost flat constant temperature line. So that is justifiable assumption, and what it helps us is that we can find out the value of Ag easily from property tables. And once we have that expression, we can simply find out the specific enthalpy of the moist air sample, CPAT plus W times Hg. Specific volume of the moist air, again straightforward application of the ideal gas equation for both air and dry air and for water vapor. The next thing that we will look at are temperatures, and when we study psychrometry, we will not work with one temperature, but we will work with 3 temperatures, and we should be able to differentiate between these 3 temperatures. The first of one of these is known as the dry bulb temperature, and that is the temperature that you will measure by using an ordinary thermometer, that is the air temperature. If you are using a mercury in glass or a liquid in glass thermometer or a thermocouple or some other temperature measuring device. We use the word dry assuming that the sensor of the thermometer is almost dry without having any liquid present around it, and that is again justifiable. The wet bulb temperature, again I will first read out the definition and then we'll try to see how to conceptualize the definition that we have just read. The temperature at which water evaporating into moist air at a given dry bulb temperature and humidity ratio can bring to saturation adiabatically at the same pressure. What is implied is that we have a moist air sample which is not saturated, and that moist air sample is brought into contact with water, and water evaporates into the air stream, and eventually this evaporation will lead to a point when the air becomes saturated, and it is done such that the entire process is adiabatic. What we can think of is a large chamber which is insulated or isolated from the surroundings, and unsaturated moist air enters the chamber and flows over water which is contained in that chamber. And as the water flows in that chamber, liquid water which evaporates into the air stream will gradually increase the humidity ratio of the moist air. Okay. Now this process, because the chamber is isolated from the surroundings and we are evaporating water, there is a need for providing the latent heat of vaporization. So, and because it cannot come from outside, that heat of vaporization is extracted partially from the air stream and partially from the water, which leads to a drop in the temperature of moist air and water. And this process will continue until we reach the point where the air becomes saturated and no further evaporation will be possible. And then the temperature that you measure at that point for air and water will be the same, and that is known as the wet bulb temperature. And again, to maintain steady state conditions, we will also ensure that we are providing water to the chamber in an amount which is equal to the rate at which is evaporating to the air stream and at the same temperature. We can look at this schematic diagram of the process that we have just looked at. State 1 is where we have the unsaturated air coming into this insulated chamber. The air stream as you move along the chamber will gain water vapor from the water contained in the chamber. Its humidity ratio will increase and there will be a decrease in the temperature until you reach the end of the chamber, at which point we assume it has become saturated. Why do we need such a long chamber of almost infinite length to achieve this condition of saturation of the air? That is because the rate of evaporation is also dependent on the concentration difference between the air stream and the concentration of water vapor at the surface of water. So this is maximum at the start, and as this concentration difference starts to decrease, the rate of evaporation of water into the air stream will also decrease. And as you move further and further downstream, that rate of evaporation will keep on decreasing. So theoretically, you will need almost an infinitely long chamber to achieve saturation conditions. The water the temperature difference between the dry bulb temperature and the wet bulb temperature is known as the wet bulb temperature. And from a knowledge of these two temperatures, it is possible to estimate the humidity ratio or relative humidity of the air, that sample which you are looking at. And that is why this is an important parameter in air conditioning. Practically, if you want to do it, we wouldn't have a huge instrument. It becomes impractical to have an infinitely long or very large size instrument to measure the wet bulb temperature. But there are instruments from which using which we can find out the wet bulb temperature, and that instrument is known as a psychrometer. And I will show you two commonly used types of psychrometer. Before that, let me just go to the third temperature, that is known as the dew point temperature. If you have a moist air sample and I want to keep the pressure and humidity ratio unchanged, if I want to keep the temperature, the humidity ratio and the pressure unchanged and still saturate the air, what I can do is I can reduce the temperature of the air until the moisture in the air separates out as fog or dew. Now that temperature at which the moisture will separate out from the air sample at a constant pressure and humidity ratio is known as the dew point temperature. I will now come to the psychrometer and show you the two instruments that are quite commonly used. One is a manual instrument shown over here, which is known as the sling psychrometer. You can see it has two thermometers, one at the top whose bulb you can see, and it is basically exposed to the surrounding air. This measures the dry bulb temperature. The temperature measured by the second thermometer over here is the wet bulb temperature, and you can see the bulb is not open to the air. It is covered with a absorbent material, and this is connected to a reservoir in which you fill water, and that water that you fill in over here will ensure that this thermometer has its bulb surrounded by a wetted absorbent material. Holding this handle, you will then rotate this upper casing, and after a while you will one will notice the difference in the two temperatures. The temperature measured by the upper thermometer will be the dry bulb temperature, which will be higher, and the one measured by the lower thermometer will be the wet bulb temperature, which will be lower. And I will show you a video how it is properly done. The other is a digital psychrometer, and we have looking at it over here. It has a display on which you can see various properties like relative humidity, dry bulb temperature, wet bulb temperature, dew point temperature, etc. And I will again show you a short video of this type of a psychrometer. So let's start with the sling psychrometer.
Hello, welcome to iYogs International's video lesson. Today you are going to learn about the use of a whirling hygrometer. The whirling hygrometer is also known as a sling psychrometer, and it is mostly used by coating inspectors to record the air temperature, relative humidity, and dew point. The hygrometer is comprised of two thermometers, which has one of the bulbs covered by a wick. The bulb covered by wick is known as a wet bulb, and the uncovered bulb is called the dry bulb. The instrument also has a reservoir. Before start using the hygrometer, a bit of preparation and precautions are needed, and these involve the following. Check that the wet bulb sensor is covered entirely by the wick. Fill the reservoir and saturate the wick of the wet bulb entirely with water. Several minutes may be needed for total saturation of the wick. Avoid touching the wick, because doing so may leave oil or dirt behind. Keep the dry bulb entirely dry. Be ecologically friendly by not whirling the hygrometer in direct sunlight or near the heat source. The correct technique for using a hygrometer is face the wind and hold the handle of hygrometer well away from the body. Whirl the hygrometer rapidly, and after 30 seconds stop the motion and quickly read the wet bulb temperature. Go back to whirling the hygrometer for another 10 seconds and then read the wet bulb temperature for the second time. Continue this system of whirling until 3 successive readings are the same or the wet bulb temperature becomes stable. When the temperature stabilizes, read and record first the wet bulb temperature. Next, read and record the dry bulb temperature. While reading the thermometers, keep your body, hands, and any warmer or colder objects as far away as possible from the thermometer bulbs. After the wet and dry bulb temperature is established, a psychrometric table or psychrometer calculator is utilized to ascertain relative humidity and dew point of the air. The psychrometric table needs wet bulb depression value. The wet bulb depression value is the difference between the dry and wet bulb temperatures. Both the dry bulb temperature and wet bulb depression are located on the vertical and horizontal axes, respectively, of the psychrometric tables. The point where the two temperatures cross indicates the relative humidity or dew point.
Next, we will look at the working of a digital psychrometer. So this is the sensor of the psychrometer, which is protected by a cap which can be closed and opened. When the psychrometer is not in use, it's closed, and when you want to use the psychrometer, you will open the cap and then start using it. Okay. That is the display of the psychrometer, and there are a number of buttons which you can see in the front. This is the on-off button. F/C, you can toggle between degree Fahrenheit and degree Celsius. The wet bulb temperature, WBT, and DEW is the dew point temperature. Hold if you are measuring changing values and you want to hold the value at a particular point, you can press this button. If you take several readings and you want to find out the maximum and minimum, that feature is also available. Okay, when you turn on the psychrometer, typically you will get the relative humidity and the dry bulb temperature, and then you can also move on to other temperature readings. Now it's giving you the dew point temperature, and that is identified by the latest DEW on the left hand side of the temperature measurement, and it's in degree Fahrenheit. Similarly, the wet bulb temperature will also be identified by the latest WBT. And this is quite a handy instrument and used to measure the desired values in the industry. Once you have used it, you can close the sensor cap and store it in its casing. So the properties, again, just to summarize, we had the total pressure, the humidity ratio, relative humidity, the dry bulb temperature, wet bulb temperature, dew point temperature, the specific enthalpy of moist air, the specific volume, and we have the relevant mathematical equations to calculate these. But there is an alternate available to us, and that is a graphical representation of these properties, which is known as the psychrometric chart. And it is quite a convenient tool for professionals in the HVAC industry. And we will first look at what information is there on a typical psychrometric chart. First thing that you have to keep in mind that the psychrometric chart is constructed for a specified value of barometric pressure, that means the atmospheric pressure. And what it means that if the barometric pressure changes, the values in the psychrometric chart will also change. And that is an important difference between the state of a moist air, that it requires at least 3 independent properties to establish the state of moist air, one of them being pressure. Once that pressure is established, we can then choose any 2 other properties, and the state of the moist air will be shown on the psychrometric chart. On the horizontal axis, you have the dry bulb temperature, and you have the humidity ratio on the vertical axis. Humidity ratio is also referred to as absolute humidity. And then there are some other curves and lines on this psychrometric chart. For example, we have a constant relative humidity line, and you can see some constant relative humidity lines over here. starting with, let's say, 20%, then we have 40, 60, 80%. And on the saturation line, by default, the humidity, relative humidity, must be 100%. Similarly, on the horizontal axis, where the humidity ratio is 0, the relative humidity will be 0. The constant specific volume lines are also shown, which will have units of meter cube per kilogram dry air. Constant wet bulb temperature lines are shown over here, and you can also read the enthalpy at the state at which you are interested in by using a scale in which the enthalpy is given as in units of kilojoule per kilogram dry air. We will be basically using the ASHRAE psychrometric chart number 1, and it has certain one additional feature, which when we look at that chart, I will show it to you. It's a more detailed chart. ASHRAE psychrometric chart number 1 means that there are other psychrometric charts produced by ASHRAE. In fact, in SI system there are 7 psychrometric charts produced by ASHRAE. Psychrometric charts number 1 to 4 are for the normal, for the standard barometric pressure of 101.325 pascals, and but for different temperature ranges. Psychrometric chart number 1 is for the normal temperature range from 0 to 50 degrees C, and it is the most commonly used psychrometric chart in the HVAC industry. The other 3 charts, 5, 6 and 7, are for different pressures. As I said, if you change the pressure, the property values change. So ASHRAE psychrometric charts number 5, 6 and 7 are for different pressures, and those pressures are specified in terms of the height above sea level, that is 750 meters above sea level. That will be ASHRAE psychrometric chart number 5. Then 1500 meters above sea level, psychrometric chart number 6, and 2250 meters above sea level, that will be psychrometric chart number 7. And 5, 6, 7 are for the normal temperature range of 0 to 50 degrees C. I will now show you the psychrometric chart that we will be making use of, and you should be familiar with the use of this table. It is a more detailed table, but it has the same information. Of course, you can see the barometric pressure shown over here. And first of all, let's look at the psychrometric chart over here and try to identify any differences between this chart and the one that we looked at earlier. And there is one important difference that you should keep in mind over here, and that is the units for the humidity ratio. Now, the humidity ratio in the ASHRAE psychrometric charts is given in grams per kilogram dry air, that is grams of water vapor per kilogram of dry air, not in kilograms per kilogram dry air. So if you are given a value of humidity ratio in kilogram per kilogram for dry air, you have to multiply it by 1000 to convert it to grams per kilogram dry air. And the other way around, if you read a value from the chart which is in grams per kilogram dry air, you have to divide it by 1000 to get the value in kilograms per kilogram dry air. Other than that, we have the usual properties that we had looked at. That means the relative humidity, constant relative humidity lines are there. The dotted lines are the constant wet bulb temperature lines. Then these lines are the constant specific volume lines, the constant specific enthalpy lines, and the scale from which you can read the enthalpy. So all these lines, constant property lines, are clearly identified on the psychrometric chart. In addition, there is another tool available to us. If you look at the top left hand side, you can see a protractor with 2 scales, one inside, the other outside. The utility of this tool we will look at when we study psychrometric processes, and it is quite a useful tool. So we will leave it for the time being, and we will come back to this protractor when we study psychrometric processes. What I would like to do is, just as an example, try to find out some properties at a particular state of given to us for a moist air sample. Let's say we are given a moist air sample whose dry bulb temperature is 29 degrees C and its relative humidity is 30%. I can mark that state over here. Look at this, we have this is 29 degrees C, and we move vertically upwards, and where this line intersects the 30% relative humidity line, that is the state of the dry air that is given to us. And at this state I want to find out the values of the other properties, and I will start with the humidity ratio. So what I can do, I can move on to the vertical axis, from this state point, and then read the value. If you look at the values for the humidity ratio, these are given in increments of 0.5 grams per kilogram dry air. So this would be, if this is 6, this is 6.5, then this is 7. So this value is 7.5. That means corresponding to this state, the humidity ratio is 7.5 grams per kilogram dry air, which becomes 0.0075 kilogram per kilogram dry air. The next property value that I want to find out, for example, is the wet bulb temperature. And again, you can see the constant wet bulb temperature lines over here. So we can refer to any of these dotted lines, and we will make sure that we select a line which passes through our state point over here. Okay. So if you look at the values given to us, this dotted line has a value of 20 degrees C, the wet bulb temperature, and this one is 15. So if this is 15, this will be 16, this is 17. You are slightly above 17. If this is 17, this is 18, this is probably around 17.2 degree Celsius. So that will be the wet bulb temperature. The specific volume we will try to find out next, and just as we did earlier, we will draw a line of constant specific volume which passes through the state point that we are interested in. And you can see this is 0.86, this is 0.87, and we are almost at the center of these two values, so it will be around 0.865 would be the specific volume. Units will be meter cube per kilogram dry air. If you want a more accurate reading, you can of course use a scale. Right now I'm just reading of these visually. Then the specific enthalpy, and to find out the specific enthalpy, do not use the constant wet bulb temperature lines as a reference. They appear to be parallel to the constant enthalpy lines, but they are actually not. If you look at it closely, for example, if I look at this line over here, you can see the two are almost parallel in this part of the psychrometric chart, but they are actually diverging. So if you want to read out the specific enthalpy, you will have to draw a line which is parallel to any of these constant enthalpy lines that we have over here. And now we can read the specific enthalpy from the scale over here. The scale has increments of 1 kilojoule per kilogram dry air, so this will be around 48.2 1 kilojoule per kilogram dry air. That will be the specific enthalpy at this state. And lastly, if I want to find out the dew point temperature, remember the definition of dew point is that we need to keep the humidity ratio constant and bring the air to saturation. And you can see how we can do that. If we are at this state, we will keep the humidity ratio constant. That means we'll move horizontally until we reach the saturation curve of the psychrometric chart. So we start with that. And we are on the saturation line. And then what we can do, we can drop a line vertically from this point and then read the value, which will be the dew point temperature, and that is around 9.3 or 9.4 degrees C. If you look at 9.4 degrees C from over here, and you can see that at the saturation line, the dew point temperature, the wet bulb temperature, and the dry bulb temperature, they are all coincident. So this is what I was just talking about, and I briefed you about that. And what we will do, we will continue with this in the next class by taking up some examples where we will make use of the mathematical results that we have obtained to find out the various properties, and also use the psychrometric chart to verify those properties. I would encourage you to get familiar with the use of the psychrometric chart. You can yourself take up print out the psychrometric chart, mark a state, and then find out the unknown properties at that particular state. So that's all for today, and we will continue with this in the next class.